So welcome. So we're going to continue with this idea about Faraday's law, and we're going to apply it to a specific component. We're going to talk about inductance. So when we have a changing magnetic flux in a loop, we will induce an EMF. Sometimes that's not desired, but we've got to know about it because we've got to accommodate it. And sometimes that's very deliberately done because we actually want primarily we want the transient effect of this inductance. So we're gonna work our way towards that. So big ideas: when a current flowing around a circuit changes, the circuit induces a back EMF in itself. So this is, just turning your circuit on messes not with a circuit to the side, not just a circuit to the side. The next circuit over will feel the effects of you turning your circuit on, but it'll also mess with itself. It's very, and that can be really problematic if you're trying to turn a circuit on, and the circuit is. Well, it's a I don't know about that, but it's a situation where it's a feedback effect, where it basically says, hey, you want to do this, I'm going to fight you every way. So we have that. When a solenoid is used as a component in a circuit, it is called an inductor. This is deliberately when you're doing this, and it's particularly significant for high-frequency current changes. And inductors cause transient effects on the flow of current, analogous to what we saw with capacitors, and they can be very useful. So there's inductance by happenstance, and we've got to know how to deal with it. And then there's inductance which is deliberate, which is, hey, I want this effect. Let's talk about inductance by happenstance. So we have a circuit. Our circuit, for some reason I drew it like a Star Wars circuit. I have no idea why I did it like this, but it's basically I think because I want to show you these. But anyway, we have an EMF, we have a switch, we have a resistor. We close the switch and current flows from the positive through the external circuit. So we have a current flow like this. There's my current flow. And that current flow causes a magnetic field. So we do our corkscrew rule. And what we find is that let's have a look. I am going into the page at that side, and I am coming out of the page there. And I'm going into the page at that side and coming out of the page there. I'm going into the page at that side and out of the page there. So there's my magnetism, which is caused by my current flow. And it is an increasing magnetism. That's the important bit. It's an increasing magnetism. These three flux lines weren't there when there was no current, and now they are there because there is a current. And the magnetic and the circuit says, "Whoa, hold on! I have a changing magnetic field going through me. I'm going to fight this." And so it says, "I need to cancel out these three. So I want a magnetic field that is that geometry, and I want a magnetic field that is that geometry, and I want a magnetic field which is that geometry." And how do I get that? I'm going to create a current flow. And of course the current flow is in that direction, and in that direction, and in that direction. How do I imagine creating this? Well, my so-called induced EMF, which is going to be in that direction. So, hold on. The act of turning on a circuit induces an EMF which is like cancelling out what you just did. That's a real pain.
So how does current flow if there's...
So why is there not stalemate,
Yeah.
There's not stalemate because it's a rate of change. And initially what you start off with is a current which is zero, and then basically it increases rapidly. And in principle it goes like that. But because of this back EMF, what happens is it goes like that. And it is a rate of change. So eventually when you're over here, there's very little induced EMF because there's very little rate of change. So this back EMF starts off strong but weakens. Whereas the EMF is always going to be there. This guy's a constant. This guy's a constant. It is just, hey, I'm the EMF. This guy depends upon the rate of change. So it starts strong, but as things slowed, the very act of slowing things down makes itself weak. So in the end, although there's the same amount of current flowing, it's not changing. So this guy goes away.
So if I'm understanding this correctly, it's because it's resisting the current flow is then lower. Because it's lower, the resisting force is then lower.
Yes.
Okay.
It's kind of like
so
it's
it starts strong and then drops off.
Yeah.
Pretty quickly. Okay, I understand.
So when is this important? This is really important when you have big changes in magnetic field going through your loop. And so if you have all circuits come in loops. So when you try and turn on big current applications, this is more significant. You'll see the effects. If I turn the light switch on, I don't notice this effect. But if I have a big current application, I will see this effect. So I think that's partly why when there's a power outage, they can't just flick a switch down at the power station and everybody's lights come on. Suddenly we've all got power. They've got to do it section by section by section, because when they flick that switch, if everybody did leave their lights on, it's a massive current draw, and that will actually trip circuits which will close them down. So turning on a circuit is a big current circuit is a problem, and ironically, turning off a big current circuit is a problem. It doesn't want to be turned off, and that's got a whole bunch of safety issues.
What do you mean? If you disconnect a circuit?
If I disconnect, then what happens is I have a changing number of flux lines going through my. So rather than creating these flux lines, I have a changing number of flux lines. Yes. So it's like, you might think you're turning me off, but you're not turning me off. So the high power, high current issues, this is an issue. The other place actually is when you have very rapidly changing signals that happen to be quite small, because even a small effect can affect a small signal. And so ironically, in integrated circuits, they have to be careful about inductance. Because stray inductance, because it doesn't take much to mess up a high frequency chain of signals, ones and zeros. It's either there or it's not. It can't get more steeper than that, in principle. So it will tend to slow down how quickly you can apply a voltage, which is a real pain. And so, in fact, when they design integrated circuits, in the very, very, very early days, they would have people who would lay out integrated circuits. The very, very, very early days. And very quickly they realized if they want 1 million transistors, they don't want a person laying this out. They need computers. And so they started writing computer programs which would lay out the integrated circuit. And these got more and more sophisticated, and sure enough, one of the things they did was just the routing of the currents into and out of the integrated circuit. These lines. You do not want these. So, for instance, if you've given a choice between having a circuit on an integrated circuit that looks like that, or a circuit on an integrated circuit that looks like that, you'll pick the one on the right, because there's less area for magnetic flux to mess with. This has a nice big juicy area, and so this is asking for inductance. Whereas this one where you've actually tried to get rid of it, where you've tried to minimize the area is minimizing the inductance. So the two extremes really, the high current power and small integrated circuits are where these things can really bite you. Turning your light switch on, you won't notice that. This diagram below is basically just a formal, better diagram of the one I did above. Okay, So self-inductance it's called. When a current flowing through a solenoid changes, a back EMF is established because it's fighting you. The back EMF is always proportional to di by dt, the rate of change of current. The EMF caused by inductance is equal to minus the number of turns in a coil, d phi b by dt, which equals minus L di by dt. We've kind of introduced this terminology L. It's an invented thing. We're going to invent it. It's called inductance. So EMF is equal to minus L di by dt. So that's a good equation. EMF is equal to minus L di by dt. It's a bit like E is equal to IR, or RI. So the L is a bit like your R, but instead of having an I, we have di by dt. L is called inductance of the solenoid. The inductance is a measure of the resistance to the change in current. L is equal to, so we can take these guys and rearrange them. We get L is equal to the number of turns, phi b, that's the magnetic flux through the solenoid, over I. The SI unit for the inductance is the Henry. Okay, is the Henry. I don't care so much about this. I'm not above giving you it and saying play with it, but don't put this in memory. Magnetic field of a solenoid is B is equal to mu naught N over, well, we said N over L in our lab, remember? But L's kind of important now to be used for inductance, so we've got to find a new letter, so we call it N over D. You think all those chapters would kind of get together, and but they can't. There's just too many terms. So mu naught N over D times I. The magnetic flux through each coil is flux B is equal to B times A times the cosine of 90 degrees, so times the cosine of 0, which is 1. So because they're at 90 degrees, because it's like that. Area vector is like that, and my B vector is like that, so they're parallel to each other. So I don't need to worry about the angle. And this equals mu naught N over D times A. So, okay. So what's going on here? I have my B times my A. Okay. If L is equal to N phi B over I, so this equals mu naught. I always let's have a look. I'm substituting for that phi b. I'm substituting mu naught, one of the n's, the A and the D, and I have another n because of that guy, and I have a I. The i's cancelled, so I get L is equal to that. And then I say, well, L is equal to mu naught. Well, rather than this N, which is the number of turns, let's call it the number of turns per unit length times the length, which is little n times D, squared over D. And then, my D's cancel, so it's mu naught N squared. And my A is there, and one of my D's is left, and so I end up with mu naught N squared A times D. And look at that, A times D is the area times the length, which is the volume. So we get that our inductance of a solenoid is equal to mu naught, which is magnetic. You expect that to be in there. And then the number of turns per unit length squared. So as you make your coil more condensed, it really increases the inductance. Doubling the number of turns per unit length quadruples the inductance. Tripling the number of turns per unit length, 9 times the inductance. So it really is an advantage if you want big inductors to wind this thing tight. And then volume, yeah. So I could have a bigger area, and not so long solenoid, or it's got to still be solenoidic, or I can have a very long pencil type one, and it's the volume that matters. Okay, so that's kind of interesting from a physical point of view, but you don't have to remember it. Just, if I want you to play with it, I will give you the equation and say, hey, what happens to this as volume changes? What does V stand for? Is it voltage or is it volume? You got to be familiar enough with it like that. Yes. No comment, no question? Okay. This is really important. It was important for capacitors, and it's important for this as well. So this is really important. Consider the circuit shown below. Consider the closing switch. So this is the circuit. Let's talk about that. DC, switch, inductor, resistor. Ignore this. It's open. It's like it's not there. The inductor is not energized. There's no magnetic field in the inductor. There's no current flowing through in the inductor. And then I close this switch. So current flows. We're going to play the game like we played for capacitors of, what's the voltage across the inductor immediately? What's the voltage across the inductor in a long time? What's the voltage across the resistor immediately? What's the voltage across the resistor in a long time? And what we can tell is that, when you first start, close this switch, you're going to have a big current flow. There's going to be, most of your voltage is going to be across your resistor. Yeah? Big current flow, V equals IR. My EMF is L di by dt. So in a long, long time, did I just mess up completely? In a long, long time, my current flow through my inductor is not changing by much. And so there's not much EMF. Oh, messed up. Initially, your potential differences across your inductor is the opposite to the capacitance. So this is at time t equals 0. This is going to be equal to my EMF, and this is going to be equal to 0. And t is a long, long time. This will be 0, and this will be my EMF. Okay. I can do Kirchhoff's laws, yada, yada, yada. I end up with this expression. What we said for a capacitor, I think the way to do this is by analogy. We said for a capacitor which was discharging, the current equal, the charge on the capacitor was equal to E times C, 1 minus E to the minus T over tau, where tau's the time constant, EC 1 minus E to the minus T over RC. Remember that? Oh, go away. Remember that? So, okay. This is analogous. So rather than Q, we have I. The maximum possible I. Well, we had E equals IR, whereas down here we had charge equals VC. So we've got the maximum. This is maximum current flow. This is the maximum charge. And it's modified by this term, which gives you the curviness to it. And it's 1 minus E to the minus T over, and in this case, the time constant is L over R. So rather than RC, we have L over R. And I don't have a simple way for you to remember that. I just don't. So, well, I suppose you could say if that's over R, that's over R, and that was times C, and that was times C. So maybe there's a way there, but you know. So again, this is energizing the inductor. It starts off with no magnetism, and then we're energizing the inductor. So our current takes a while to get there. Starts off with no current because I'm fighting it, so no voltage drop across the resistor. ends up with a lot of current because it's in steady state, all the voltage drop is across the resistor. So, and we have the tau is the 63% mark for energizing, for the current to flow through. And by analogy, we can have the de-energizing, where basically we disconnect our power supply and we let this current flow down to zero. So we close this guy, let the current flow down to zero, and whoosh, it goes away. And for this one, I just remember it as it's the one. This is the complicated version because it's 1 minus, and this is the inverse of it. So it's just the 1, not the 1 minus, it's just the e to the minus. And that is t, okay, yeah, so I don't like that. Minus t over tau, I wish I'd said. And that tau is equal to that. It's mathematically correct, it's just, I think it's making it more complicated. So know those. Just like you did for capacitors, okay? A bit of conceptual stuff. So which one is the two traces, current versus time? Which one of these has the bigger inductor, the red circuit or the blue circuit? It would be the red, actually, because it's slowing you down more. Yeah? The more the inductance.
Well, that's the actual current flow of the battery.
This is the current in time.
Okay, right, that was not
Yep.
yeah.
Yeah, cool. Yeah. So it's it's a bit intuitive there. Let's do this. What's the time constant of a circuit that consists of a 5 Henry? This is 5 Henry and 9 ohms. 9 ohms. And what was it? It was tau is equal to L over R. Yeah, the R is on the bottom. And I can kind of remember that by I is equal to V over R, and R is on the bottom, so I'm going to kind of remember it like that. I'm going to try and get that in. So this is going to be 5 over 9. Oh, beautiful choice. Which is 5 9s are 45. So is that 5.5? 0.55? Seconds. Okay. So that's really good. If I ask you for 20 seconds, you're basically saturated out. And if I ask you for, instantaneous, you're at the beginning. So it's a very nice way of figuring out how significant, how long this transient effect is. Consider this circuit that consists of a 2-volt battery. So that's 2 volts. This is a 4 Henry inductor, and it is a 7 ohm resistor. Connected in series, when the current flows through the resistor, 30 seconds. So there's the smart way and the not so smart way. I'm charging up. So my I is equal to, what did we say? It was equal to E over R, which equals 1, which times 1 minus e to the minus t over, what was that? L over R. And you can substitute. Or the other way is you turn around and say, well, tau is equal to L over R, which equals L, which is 4, over 7, which equals 0.57 are 35, put down the 5, carry 5, 7 7s are 49 seconds. And we have 30 seconds. T is very much greater than tau. So what is the current flow? I is equal to, and it's going to be E over R, which equals 2 over 7. I is equal to 0, 2 7s are 14, 60, 7 7s are 49, 8 7s are 56, 8 7s are 56, 4, whatever, amps. That's one way of doing it, using your noggin. The other way is you turn around and say, oh, well, it's going to work. So that's 2 over 7, just like I had over here. 1 minus e to the minus 30 over 0.57. And you can work that out. This here, get your calculators out. Did I bring my calculator this morning? Shame. That's not like me. If you work out e to the minus 30 over 0.57, you're going to get, it's going to be like 0. Yep. Something to the minus some 23 or something, yeah. So it's a 0. So then the I is equal to 2 over 7 amps. And either way works. It's just one way you're seeing, you kind of seeing more. Okay. What is the energy inside an inductor? As with, well, actually this is not bad. What was the energy inside a capacitor? Was it that? Energy inside a capacitor? I can figure this out. Q versus V goes like that. Oh, half Q. Now, half CV, which equals a half Q times V. I think it is a half CV squared. Yep. So you can always see by analogy, you know, it's kind of like it's similar. But again, I'm not that worried about it. It's kind of like battery must do work against an inductor to establish an electric current. Part of the energy supplied by the battery appears as an internal energy of the resistor. The remaining energy is stored as magnetic field. The resistor gets a little bit warm, and you have a magnetic field here. So you're storing energy via the magnetic field. Kirchhoff's law says this is the loop rule. So the EMF, and we've got to take into account the potential difference across the resistor and the potential difference across the inductor. And then we do some math. We multiply both sides by I. Sorry about that. That's part of that sentence. So we get I times E and I squared R and that. And then if you remember, du by dt equals Li di by dt. I don't remember that, but I can believe it. So then I go, well, d, the total energy stored is the integral of this, which gets me to that. Okay, so let's think about the physics of it. If I have a certain inductor with a certain current flowing through it, and I double the inductance, I get twice as much energy stored. That makes sense. What's more interesting is if I double my current, I get 4 times the energy stored in it, etc. So know what that equation is about, but don't commit it to memory. When one of the equation sheets, it was fair game, but now it's not. I've got to make some choices. This next bit also, when this was on the equation sheet, it was fair game, and you'll find some old questions about it. But here, I would just want you to stick to conceptually. Yes, if I have a changing current in one coil, I have a changing flux through the other coil, and so I have an EMF induced in that second coil, and the second coil induces an EMF in the first coil. So we had self-inductance, but we also have mutual inductance, and that makes sense. We did all that stuff with the 2 coils talking to each other. That's mutual inductance. And it's kind of interesting, rather than calling it L for the inductance of itself, we call it M for the mutual inductance. And the mutual inductance in coil 2 is caused, the number of turns in 2 times the flux through 2 over the current in 1, the thing that creates it over the thing that results. You know that equation's there, but we tend to use this for transformers, and the using transformers is pretty straightforward. And again, continuing, okay, the EMF caused by mutual inductance E is equal to, rather than before for inductance, we said that E is equal to minus L di by dt. We're just using M rather than L. Again, know it's there, don't commit it to memory. we're going to make a circuit. It's a theoretical circuit. It has an inductor and a capacitor, no resistance. You can't make a circuit without resistance. Even the inductor has wire in it, so there is some inductor, there is some resistance, but for the sake of the argument, we're going to pretend like it's so small, it's so insignificant, it's untrue. And if it's just sat on a bench, nothing's going to happen because it's just, there's no energy in it. I can put energy into it by charging this guy up. And then I can just let it go. So I put charge on the plates, the capacitor, and then I just let the system go. And we know that the positives are going to try and combine with the negatives in the external circuit, and so we're going to get current flow. We know that there's going to be a rate of change of current flow, and we know the rate of change of current flow is going to, well, the current flow itself is going to cause a magnetic field. And the magnetic field has energy in it. So can you see how we're going from no magnetism in the inductor, meaning no energy stored in the inductor, and all the charge on the capacitor, meaning all the energy is in the capacitor. And then we go to a point where we have current flowing, so we have magnetic field in the inductor, so energy storage in the inductor, and no charge on the capacitor, so there's no energy in the capacitor. And then you're going to recharge the capacitor in the opposite sense, because it's going to flow through and recharge. What was positive becomes negative. No current flow. And then it's going to unwind again. So you go, the current flows one way, and then back again. And then one way, and then back again. And so we get, mechanically, it's like a mass on a spring. And so we say, assume a capacitor is fully charged, so initially all the energy is stored in the capacitor. When switch is closed, the capacitor discharges through the inductor, a current flows through the inductor, the current reaches a maximum as the capacitance becomes fully discharged. At this point, no energy is stored in the capacitor, and all the energy is stored in the inductor. The current flow continues at a slower and slower rate as the capacitor becomes charged with the opposite polarity to what it started off with. Eventually, the capacitor is fully charged and the current flow is zero. At this point, all the energy is in the capacitor again, and it continues backwards and forwards. It's going to have a natural frequency just like a pendulum does, just like a mass on a spring does, and we can use these analogies. So we're going to get simple harmonic motion, and all that stuff is going to be the equivalent. Okay, so the total energy in an LC circuit, and I've got to tell you, we're just going to look through this, and I'm going to use an analogy at the end to get a value out. But if it's there if you want it. How much time do I have? Oh, not so. I've got 10 minutes to struggle through this. So our total energy is energy of an inductor plus our energy of a capacitor. And this is a half Li squared, and this is a half Q squared over C. So U is equal to that added together. Then this theoretical circuit has no resistance, so no energy is lost to heat. So resistance is like friction in a mechanical circuit. So the total energy does not change, so du by dt is 0. So, okay, du by dt equals d by dt of what we just figured out. And let's have a look. And so this is, well, the L's constant and the 2's constant. So this is L over 2 times d by dt. And let's write it for some reason as I times I rather than I squared. That's just a rearrangement. And then let's take this 2 over c because c's constant. And then let's do d by dt of q times q. And then this is L over 2I di by dt plus di by dt times I plus 1 over 2cq dq by dt plus dq by dt times q. So we end up getting, so this is 2L over 2I di by dt plus 2 over 2c dq by q times dq by dt, which equals Li di by dt plus q over c dq by dt. And then remembering that this equals 0, we get I, and the I is equal to the rate of change of charge with time, and that the I by dt equals d2q by dt squared. We get the u by dt is equal to li d2q by dt squared plus q over c times I, and let's have a look. Dividing by I gives L d2q by dt squared plus q over c equals 0. And rearranging gives d2q by dt squared is equal to minus q over lc, which equals minus 1 over lc times q. So I'm kind of getting this out as a factor times c. And if I look at this, this is said to remind me of my mechanical days, physics 1. So d2q by dt squared equals minus 1 over lc times q, which looks like d2x by dt squared, which equals minus k over m times x, which equals minus omega squared x. And so, minus omega squared x, and let's have a look, k over m and all that. For the mass on a spring, we said that omega equaled root k over m, and the solution was x equals a cos omega t plus phi, where phi is the phase angle. So by analogy, for an RC circuit, Q is equal to, well, Q max, a cos omega t. So we're stealing that little bit. And then, what's our natural frequency? Again, using that bit, looks like that bit, we get, it's square root of 1 over LC.
I assume it's supposed to be LC circuit, not RC circuit?
This is an LC circuit. Did I say RC circuit?
Yeah, it's right for, no, go to the by analogy.
By analogy.
Third line.
Third box.
Third line?
I assume
Yeah. No, nice. Thank you. Yeah, thanks. That's an LC circuit, yes. And if you want to know the current by differentiation, dq by dt equals that. So we're going to basically use all the math we did for circular motion, and we're going to steal it. Okay. And you don't need to, what do you need to get out of that? You need to get that. You need to get that. And I suppose you need that, but so to determine the phase angle, what we say is, how far are we out from where we should be? Consider the solution to that. I don't care about that. Okay. So on this, these are going to come up, okay? But they're not on my mind yet. Not in this chapter. We're going to get to them, but not in this chapter yet. I don't care about that. I don't care about that. I'd gladly just miss it out, but then you'd go to the next stage and you'd say, I've never heard of mutual inductance. And they'd go, what kind of school did you go to? So, not going away. That, be able to play with it, but you don't necessarily need to know it, but do know how to do this. Conceptually and mathematically, know these two equations. I don't care about that particularly. Know these guys. So not so much from this chapter, but we're laying the foundations for future chapters. Any questions?